Recording. Okay, so darn it, I just did it again. We're doing office hours. Most of the questions we're looking at Chem 129 questions. The 124 folks are working on making their graphs for labs and things like that. So we got some questions from 2.1, 2.2, and 3.1 to work through. We'll just go down the list, starting with 2.1, number 24. I need someone to remind me what that question is.
Mine said, consider a solution that is made from mixing 0.044 moles of A plus and 0.079 moles B minus in 125 milliliters of water. If AB solid form has a KSP of 1.6 e to the negative 8, what is the concentration of cations and anions at equilibrium in molarity?
What is this doing?
That's why we're here.
So let's look at the things that give us hints inside of the problem to begin with. Right? It says AB solid forms, and it gives us values in moles. What does that suggest to us?
Precipitation?
Yeah. So the first thing that happens is we're going to do some stoic with precipitation, right? We need to use the context of the problem to help us kind of figure out what's going on. We need to recognize that we're given moles and we're told the solid forms. Those are all hints for the process of what we're supposed to do. So we say, okay, I'm going to be doing some stoichiometry. Then what does the question tell us to do? What's the other piece it tells us to do? Or what's it asking for?
Concentrations of cations and anions at equilibrium.
And then it says we're going to do something at equilibrium. So we're going to do some stoichiometry. We're going to form some solid. Then we're going to look at the equilibrium of that solid. We did a problem pretty much like this last Friday. Let's do another one. Let's go ahead and do it. So this one's pretty nice because it's a 1-to-1 ratio. I'm going to do this in two different colors to distinguish the two different bits going on. We're going to have A plus B minus goes to AB solid. Part 2 is going to be the equilibrium. So I've got, notice it's already given to me in moles, so I don't have to do any weird conversions. 0.044, 0.079. It's all 1-to-1 mole ratio, so I can tell this is going to be minus 0.044, minus 0.044, plus 0.044. It's all in moles already, so nothing there. I know how much solid I made. Unfortunately, the question doesn't ask us anything about the amount of solid made. I can find the amount of excess B.
Would it be different molarity though because it's not a liter of water?
Well, this is all in moles right now, so we haven't done anything.
Haven't done moles. Or we haven't. Okay.
We haven't converted yet. This is all in moles. You're thinking a step ahead.
Okay.
We're about to do that part. 0.079 minus 0.044 gives me 0.035 moles of excess B. So on the surface of this, if we were just doing a Chem 127 class, we'd say A plus is 0, there's no cations left. B minus is 0.035 moles. I could divide by the volume. That would get me molarity, and that's how much that would be left. However, we know because we took Chem 128 and we've been in 129 for 3 weeks, that we also have to consider the equilibrium of this thing not actually being 0, but only being approximately 0. So then I can go ahead and do my equilibrium step, where I'm going to consider how much does this solid redissolve, or how much of the solid doesn't form, how much does it redissolve, how much disassociates to make it so that 0 is not 0. So I'm going to look at AB solid, going to A plus B minus. This is going to be approximately 0. This is going to be 0.035 divided by 0.125. There's that conversion to molarity. Because when we're doing our equilibrium calculation, we want it in molarity. 0.035 divided by 0.125 That gets us 0.28 molarity. I didn't really give myself enough space for that. I'm going to rewrite that. 0.035 divided by 0.125 equals, did I erase it? No, good. 0.28 molarity. So I've got some molarity. I don't really care about the solid being formed, the solid dissolving. We'll get to that idea in a moment. I'm going to have plus x. I'm going to have x, and I'm going to have approximately 0.28. Using the x is small approximation, which I feel comfortable with because my KSP value is pretty tiny. At this point, now I'm just solving an equilibrium table, right? And I know y'all can do this math. The thing that people have trouble with is this kind of thinking at the beginning of what are the clues, what are the cues, what are the terms that let me know that stoichiometry is happening. What are the clues, cues, terms, ideas that let me know I should also do some equilibrium? How do I know which order I go in? How do I know which compounds I'm considering? The setup is where most of you have trouble, right? Once I set this up, it's easy, right? I can have you, oh yeah, I'll punch into your calculators, and it's just like, yeah, of course I can punch things into my calculator and get a number. It's how are you thinking about it to frame the problem and kind of looking at the information given, guiding you to what the problem is, or the process is to solve the problem. I'll go ahead and finish solving it real quick, just so we can get our final answers. I'm going to have 1.6 times 10 to the minus 8 is equal to 0.28x, just bringing those things over. I'm going to get x is equal to 5.71 times 10 to the minus 8. My B concentration is my anion concentration. My concentration of B is about 0.28. I need to do the stoichiometry to figure that out. And then my A value, my cation concentration, is going to be this equilibrium value. That is not 0, but is pretty darn close to 0. Right? Approximately 0 is pretty reasonable for this. But the problem wants us to calculate the exact and not the approximate.
So it's approximately 0.28. Like it's technically 0.28 plus 5.7 times 10. But
yes.
For rounding, it's still the same.
Yeah, yeah.
Okay,
so it would be 0.280000057.
Okay.
We just call it 0.28. Any questions on that one? Yeah.
I think just general question. I have personal questions about the class. Can I just shoot you an email? And
Yeah. Oh, you should have said something earlier. I'll pop out. I'll have you all get started on number 6, and we can talk real quick.
Yeah.
Let's set up number 6, and then I will have a conversation while you all work on number 6. What is so this is switching to 2.2. Number 6. What is number 6 on 2.2? Someone read it out to me real quick.
Lactic acid C3H6O3 occurs in sour milk, such as in foods, yada yada. pH, aqueous solution, 0.1 molar lactic acid, and solution is 2.43. What are Ka and pKa of lactic acid?
What's the concentration again?
2.43.
No, that was the pH. What was the
0.1 molar.
0.1 molarity. That was the part I missed. Okay. So we know it's lactic acid. We know it's pH. We know the initial concentration. Now, the idea of pH should not automatically, but the idea of pH should make us think, oh, there's some equilibrium going on. Because we measure pH at equilibrium. So there's some equilibrium table that we have to set up for lactic acid in solution. I'm going to let you all start working on that, and we'll come back and talk about it in just a moment. How did we do with number 6? Figure it out? Let's do our logical thinking, right? So at the surface, it's like, well, what do we even do with this? We've got 2 numbers, and that's it. But we've got a chemical compound. We know we're putting lactic acid into solution. So we say, is there a chemical reaction? maybe, kinda, but really it's an equilibrium, right? It's how does lactic acid interact with water? That's the definition of Ka. So we're gonna set this up. I'm gonna use a shortcut. I'm just gonna call it H-lac. This is the lactate anion, where I'm using, what is the formula for lactic acid?
C3H6O3.
So this is what I'm using for my, that's what, when I put LAC minus, that's my lactate anion that I'm talking about. So my H-lac with water goes to lactic anion plus H3O plus. Right, we've got proton donor, proton acceptor. This is 0.1 molarity. This is 0, this is 0, minus X plus X plus X. 0.1 minus X. Doing that on purpose, X and X. Now, I don't know the Ka value for this, right? Theoretically, I'm supposed to figure out the Ka value. So I'm not going to use the X small approximation, but that would mean, right now, the problem is impossible. But I haven't used one of my pieces of information yet. What does pH tell me?
The H3O constant.
Yeah, so pH gets us to concentration of H3O plus, which is going to be my X value. So when I set this up, and I have Ka is equal to X squared over 0.1 minus X, if I know what X is, I can just plug it in and solve. And that's what we do. We use pH to figure out what the X value is. And then we just plug it in and solve. We solve for the Ka value, take the negative log of the Ka value, gets us pK.
What is pKa used for? Like, why do we want to know that? Because
so it
why
turns
would
out,
we take the negative log of pK?
so it's similar to the same reason we take the negative log of the H3O plus and talk about pH. When we start looking at all the Ka values, they're all on the order of like 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, and it becomes easier if they just become 4, 5, 6, 7.
Okay.
And so we use the pKa as a reference way to talk about the pHs, the acid strengths. And it's going to be particularly useful when we start doing titrations, because there's going to be a few times when the pKa is directly in the titration. We're like, oh, that's the point where it's pKa.
Okay.
And it'll be like really nice.
Okay.
Questions about number 6? Yeah.
So for you to convert it to the H3O plus, you would have to do 10 to the negative
Yep.
of the pH?
Yep. So it is, this stuff up here would be 10 to the negative pH is equal to H3O plus. Precisely. Yeah.
And for the 0.1 minus X, are we assuming then that X is not small? Is that why we're
We don't need to do the approximation here. We know what X is. So if we don't need to do the approximation, let's not do the approximation. Right? We know the X value because we're given that pH. And I'm pretty sure the problem has like a weird quirk where if you use the X small approximation, it's like, hey, do you need to do that?
Yeah, it does.
Yeah, okay. I programmed that in on like Monday or something like that because somebody asked me and I was like, oh, I should probably give a hint. Oh, it's with you. Yeah. So it now has that hint. So if you use the X small approximation, it's like, don't do that. Now, a lot of times we don't know what the X value is, so of course we use the X small approximation. Here, you know, if we don't know the Ka value, if you remember today in class when I didn't know what the Ka value was, I was really anxious about using the X small approximation. I think when you look at it, 10 to the negative 2.4, the X small approximation is not even that bad in this case, but we don't need it. Don't need it. Any other questions about this one before we go back to 2.1 number 5? Yeah.
It's not about this, but it's actually just a quick question.
Sure.
One of the problems I have in LabPal, and is the difference between using stoic and using equilibrium concentrations, is there wording that's really gonna let me know which one to use?
There's going to be certain things that we look for, and this is a big problem. This isn't with LabPal. This is with quizzes, exams, content, sample problems, everything. It's always like, when do I use stoic? When do I use equilibrium? Almost everything we do has equilibrium at some point. Since we're not doing simple stoic anymore, we're always trying to make sure we take that energy into account. The thing that we're looking for that gives us the hint that stoichiometry is happening is we're looking for anything with a large K or KEQ, anything that's going to make a lot of products. So that's where our precipitation reactions are usually very large equilibrium constants. So when we do our precipitation reactions, we're going to be doing our stoichiometry there. If we do a weak acid with a strong base, strong things are very much towards products. So those strong reactions are going to make like all products. And so those situations we're going to be doing stoichiometry first. So we have to have a little bit of chemical thinking in order to figure out when we're going to do that. It's not. The other things that you can look for is there are some certain word hints. If it says how much is formed or how much is made, like that, those how much questions are often stoichiometry.
Okay.
And then it's how much in solution at equilibrium or concentration at equilibrium. Those are usually the...
Because like the last question, I had like 24, you kind of just did stoichiometry at first. You did stoichiometry at first and then went back. I did an equilibrium to see what would form right away, and then I subtracted that from the previous ions. Like I did that first, so I was like, oh, then this will form, and then what's formed, everything else is left over, blah, blah, blah. You know.
Yeah. So that becomes an issue of thinking, well, what's in solution to react? You have A minus and B, you have A plus and B minus in solution to react. You don't start with A, B in solution to disassociate. So that becomes like the order of operations type
Or then
idea.
I thought to put 1 over the KSP, like to do the reciprocal to find that,
and then you got,
and then work it backwards. And then,
so you did the 1 over the KSP to find the reverse?
that was what my thinking was. I think I gave up on that prompt.
I thought the same way.
No, that way actually works. The problem is your 1 over KSP is a giant number, so you can't use the excess score. You can't use the excess small approximation. You have to solve the quadratic. And so it becomes a total mess. You have to solve the quadratic with something that's like a billion, right? Because like it was 1 over 10 to the minus 8, so you end up with 10 something to 10 to the positive 8. It becomes a mess. And so our trick to not solve that in terms of a direct equilibrium is we say, well, let's just assume, since this is a really big number, let's just assume it goes all the way to the end, and then do it backwards a little bit. Even though going all the way to the end we know isn't exactly right, the math ends up way easier.
Yeah, you thought 1 over the KSP. I thought, okay, I'll do the reciprocal, and then I'll...
Yeah, because like, that's what we learned in 128 is like if you have the opposite, then you can just do 1 over the K.
Yeah. So that is just a matter of since you have that large K, X is large.
Right.
You can't use any approximations. You have to solve the quadratic in that case. And usually, you have to solve the quadratic and keep something like 7 or 8 sig figs.
Right.
Because your one of your compounds, A or B, is going to go to approximately 0. And so you have to do a lot more sig figs than you actually have accuracy for.
Okay.
So again, it just, the whole point of doing this stoichiometry, whenever you see a really large K value, you just think, oh, I'm going to do stoichiometry. Come on in, there's space up here. Whenever you see a really large K value, you should think, oh, I'm just going to do stoichiometry and look at the flip, because then I can use my approximations. Okay, let's look at 2.1 number 5 real quick, and then we'll go on to 3.1. Does someone have 2.1 number 5 up so we can get the wording on it?
It's kind of long though. That's okay.
Oh, let me take a look then. 2.1, oh, yes. So this is actually really similar to the AB problem that you walked in while we were doing, right? This is solid forms. We have to do the stoichiometry for how much solid forms, and then it dissolves. The reason this one is so long is because it's walking it step by step. Rather than just being like, just tell me the end of it. It's like, well, hold on, let's think through this step by step. So I'll go ahead and I'll set this up. This is, consider a solution that's made from mixing 35 milliliters of 0.22 molar AgNO3 with 83 milliliters of 0.22 molar Na2SO4. Now, the solid equilibriums here, this silver nitrate and sodium sulfate, these are both incredibly soluble compounds, so their like solid forming equilibriums aren't going to matter. It's just pretty much going to be putting Ag plus into solution, and it's pretty much just going to be putting SO4 2 minus into solution. Then we look at this and we say, well, if those two things are solution, I probably need to do this in 2 steps. I'm going to have to do step 1 is doing some stoich. Right? Often, here's another thing that we can look for stoich. Often if I'm adding cations to anions, a reaction usually happens. Right? So I'm going to look at my stoich for precipitating. And then I've got to look at equilibrium. And then I have to look at the equilibrium to fix my overestimation, right? If I do the stoichiometry without my energy terms, without my equilibrium, I'm going to make more products than I should. And not physically, I mean in my calculation, I'm going to have a number that's bigger than reality would make, and then I have to fix it with the equilibrium. So the first thing we do is we do our, here, I'll hand this back to you. So we can kind of do this in a couple steps. First, we're going to set up our stoichiometry. This is going to be Ag plus 2Ag plus SO4 2 minus goes to Ag2SO4. I got to convert my concentrations to molarity, so I'm going to do 0.035 times 0.22, just converting to liters in my head. 5 times 0.22. That gets me 7.7 times 10 to the minus 3 moles of silver, and 0.83 times 0.22. That gives me, whoa, that doesn't seem right. Oh, 0.083, that's why. That's better. I'm going to do it a little bit weird. I'm going to write it as 18.26 times 10 to the minus 3 moles. In the not too distant future, I'll start using millimoles, so I can just drop that 10 to the minus 3 and call it a milli. Drop the 10 to the minus 3 and call it a milli. 2-to-1 ratio, this is the lower number, so I'm going to have minus 7.7 millimoles. I'm going to have minus 7.7 millimoles times a 1-to-2 ratio, and plus 7.7 times 10 to the minus 3 millimoles times a 1-to-2 ratio. This one has a 2-to-2 ratio. Good so far? Always label the table so we don't get confused between stoichiometry and equilibrium. Start reaction excess, I've got 0 excess there. 18, okay, so what is, oh, I'm just going to punch it into my calculator. Minus 7.7 times 10 to the minus 3 divided by 2. This is going to get us 14.41 times 10 to the minus 3. And this will get us 7.7 divided by 2, 3.85 times 10 to the minus 3. Right, so I've got how much silver sulfate solid I make in moles. I've got how much excess sulfite I have in moles.
Just quick question, you're doing the times 1/2 because that's SO2, or SO4 2 minus is the limiting reactant.
Ag is the limiting reactant. Coefficient of the limiting reactants on the bottom of the mole ratio. So
Right, okay.
this is silver's coefficient, sulfate's coefficient.
And you, even though there's a 2 Ag, oh, so it's like if there was a 2 SO4 minus,
Then the 2 would be on top.
then the 2 would be on top, and you'd kind of have
Yeah.
to see.
So essentially, every mole of silver that we uses up a half mole of sulfate. I need 2 moles of silver to react 1 mole of sulfate.
And in addition, you have more sulfate to start with.
And I have more sulfate to start with.
So it's like for sure.
For
easy to
sure.
tell what the limiting reactant is.
Yeah. Again, I checked the limiting reactant in my head. Okay, so that gets us our stoichiometry. I'm going to go ahead and write the important numbers up here. And I'll erase things. We're going to have 14.41 times 10 to the minus 3 moles of SO4. In how much is this total? 83.35 plus 83 in 118 milliliters. And I'm also going to have 3.85 times 10 to the minus 3 moles. Ag2SO4 solid. Right, that's my important results from the stoichiometry. And I'm going to go ahead and erase the stoichiometry and do the equilibrium.
Wait.
Whoa.
Don't we have the, isn't A and B the, wait, isn't A what we just solved for? Is A what we just solved
Probably.
Yeah.
Yeah, B is asking a molarity of excess.
Okay, so molarity of excess, take those two numbers, divide them by each other. So we've got, what was part A asking for? Moles of solid formed?
Yeah.
Yeah, so, yeah, I didn't even read what it was asking for. I was just like, let me think through all of the things we could do with this. And, you know, it's just in the process of thinking about it, I'm solving all the parts. So A is going to be that number of moles, B is going to be those two numbers divided by each other, which we're going to need for doing the equilibrium. So at this point, the stoichiometry is done. I'm keeping these numbers in green, erasing this work down here. We say, okay, well now I've got solid in solution. I've got 0 silver ions in solution, which can't be real. There's got to be some equilibrium going on. And the only thing I have to do equilibrium is silver sulfate. That's the only place I have for silver to come from. So I'm going to go ahead and set up an equilibrium of Ag2SO4 going to 2Ag plus SO4 2 minus, where my SO4 2 minus is going to be 14.41 divided by 118. This has a 10 to the minus 3 moles. This has times 10 to the minus 3 liters. So notice the 10s to the minus 3s just cancel out. Right, because when I convert milliliters to liters, there's the 10 to the minus 3, 10 to the minus 3. Whatever the case, I calculate a concentration here that is not 0. My silver is approximately 0. 14.4 divided by 118.122. I'm going to have plus 2x plus x. I'm going to have 2x. I'm going to have approximately 0.122. And we're back to just solving an equilibrium table that we've done before. I should find a concentration of silver that is really small but not 0. Good?
Yeah, the question I had most problem was the moles of redissolved solid.
Oh, yes. So the final question we have is, where did the silver ion come from, right? We solved for our x value. Let's go ahead and solve for our x value real quick. What's the KSP for silver sulfate? Has anyone got that handy? There it is. 1.5 times 10 to the minus 5. 1.5 times 10 to the minus 5 is going to be equal to 2x squared times 0.122. I solve for x. Is that still on screen? That's still on screen. Solve for x. 1.5 times 10 to the minus 5 divided by 0.122 divided by 4 square root. 5.54 times 10 to the minus 3 molarity. I'm going to go ahead, I'm going to multiply by total volume. Times 0.118. That's going to get me 6.54 times 10 to the minus 4 moles. Now, what do these two numbers that I just calculated mean? This is the concentration. This is the amount of silver sulfate that dissolves per liter of solution, right? This X was set up so every silver sulfate that dissolves gives me 2 silvers and 1 sulfate. So this value that I calculated is the moles of silver sulfate dissolving. If I multiply that by the total volume, that gets me the number of moles of silver sulfate dissolved in my solution, rather than just generically per liter. So that's the number of moles of silver sulfate that dissolved. If you look at the amount of solid we made and compare it to the amount that dissolves, it's actually quite a bit. Right? If I take my original, if I take the amount that dissolved, the 6.54 times 10 to the minus 4, and I divide by 3.85 times 10 to the minus 3, I end up, oh, that's not that bad actually. It's like 2%. Right? That's not nearly as much as I thought. It's like 2% dissolves. Right? So I'm taking this number of, like, I take my concentration of ions in solution. I say logically, right? There's not, the math is easy. I just multiply. But logically, I know the amount of ions in solution relates to the solid that dissolved. So I can use that ions in solution to figure out how much solid. Now, dissolved is a bit of a weird term. There's a couple different ways I refer to it, and the way I do it now is I like more. That's the amount of solid that never actually formed. Right? When we did our stoichiometry, we knew the number we got was bigger than reality. And that is how much bigger than reality it was. So it's not like that solid forms and dissolves. That's the amount of solid that never actually forms. That's the amount of solid that we overestimated by in our stoichiometry.
So the difference between that and the percentage, how would you, because you're giving us the values for the percentage, how would I do it for the moles of redissolved solid?
Oh, it would just be that number.
Okay.
It's just that number.
Yeah, that makes sense.
Does that make sense? Cool. Let's go ahead. Let's set up. Any other questions on this one?
So I know you just went over this probably, but I'm still trying to grasp it. So like when you say redissolve, so like you
In quotes.
yeah, and so the X you solve for is the amount that actually dissolves, right? The moles that actually dissolve.
Yeah. Right.
Like in a liter.
Yeah, that's the moles per liter that would dissolve if that amount of solid formed. If that amount of solid formed.
If that amount of solid formed with the same amount of solid form that dissolved, that's fine.
No, because there's an equilibrium for how much dissolves.
Right, so not, right, okay, so that amount of solid formed.
That amount of solid formed in our stoichiometry that we knew was wrong.
Right, okay.
We knew it was an overestimation.
Okay, and so the amount dissolved, I sort of get it.
Yeah.
It's
So
like that's the molarity that actually dissolved. That's not the amount of solid that actually formed. X is the amount of molarity. Like,
that would be in solution still.
That would be left. X is the amount that would be left.
In solution, yes. So you notice 5.5 times 10 to the minus 4. We originally said our silver was approximately 0. It's not actually 0, right? We said there's no silver in solution.
Right. Okay.
There's actually, well, it would be double that number, but there's some amount of silver left in solution. Where did that silver in solution come from? There's two ways to think about it. The way that it's worded in the problem, and maybe I should change this, is, oh, this solid we formed dissolves to put it back into solution.
Okay.
But in reality,
it
never actually forms, right? This is the amount of solid that never actually forms.
Okay, and
if
then
that
you
makes
multiply
sense.
it because you're not doing 1 liter.
Right. We're doing
Got
like
it. Okay,
118
that makes
liters.
Okay.
Milliliters. Okay.
And the difference between that and the net amount, so the net amount, I would just add the amount redissolved with the amount that form?
Add or
Multiply?
Divide. Or
Subtract?
which one is it? It's one of those four.
Subtract?
Why subtract?
I mean, if it's the net amount, probably then you would want to subtract it from the total
Yeah.
amount that you would most
Yeah.
likely get.
And we knew that when we did our stoichiometry without equilibrium, we knew that this number was going to be too big because we know the equilibrium would make it so that 0 wasn't 0. So this number has to be a little bit smaller than we got it. And that's how much smaller. So yeah, subtract. Ready? Okay, let's get to 3.1. And again, I'm going to set up a problem and I'm going to check on the hallway, folks. Make sure that they're not languishing out there with Excel. They're doing Excel work. What would you rather do, this or Excel work? Oh, some mixes there. Okay. So 3.1 number 2. If someone wants to read that out to me, we'll get it started. Number 2.
Use Ka and Kb values. How many grams of HF must be dissolved in water to create 777 milliliters of a solution with pH of 2.47?
How is that enough information to do a problem? You know what's funny about this? Do you all see how this is the same thing we just did? Now, we've got our hints here, right? We know it's HF in water, and we've got a pH. pH should make us think some equilibrium. This number is going to give us our H3O+, which is to say this is going to give us what we normally call X. So we're not going to need the X small approximation, but we're going to have a different unknown variable. Do me a favor, I'm going to pause this, I'm going to check with the hallway folks. Set it up, see if you can figure it out, and I'll be right back. Okay, that took me a while, sorry. So let's look at number 2. It looks like most of you got it. Thumbs up if you got it. Excellent. A couple people still looking scared. So what we got is HF plus H2O goes to F minus plus H3O plus. This is the thing, and you'll notice I start doing this kind of silly thing because I just don't know what it is. I don't know what the HF is. I don't want to use too many X's, so I just put question mark for the thing I'm trying to solve. I'm going to have minus X plus X plus X. I'm going to have question mark minus X. I'm going to have X. I'm going to have X. I'm going to set up. So Ka is equal to X squared divided by question mark minus X. And you notice we pretty much always get into some structure like this, where there's 3 different things we're trying to figure out. We're either trying to figure out A, we're trying to figure out X, or we're trying to figure out initial concentration. So we often get into situations like this. Here we know what the X value is because we've got that pH. We can look up the Ka value, and then we can solve for question mark. Let's go ahead and do that real quick. The Ka value for this is
6.8 times 10 to the negative 4.
let's go ahead and solve for what our X value is equal to. That's going to be 10 to the minus 2.47. .38 times 10 to the minus 3. So this is going to give us 3.38 times 10 to the minus 3 squared divided by whatever that question mark is, minus 3.38 times 10 to the minus 3. Notice I end up with only one variable to solve for. Mathematical operation order matters and can make our life easier. So the first thing I do is I just switch the tops and the bottom, so I end up with question mark minus 3.38 times 10 to the minus 3 is equal to 3.38 times 10 to the minus 3 squared divided by 6.8 times 10 to the minus 4. right? So that right-hand side is just going to give me a number, and then I add 3.38 times 10 to the minus 3 to it. I've seen students do all kinds of things where they like take that over, they FOIL it through, and then they like recollect terms, and then they divide back through, and it's like, yeah, you could do it that way. But paying attention to our order of operations can simplify things. Right? Because like first instinct most people have is you multiply the bottom over and then FOIL. And it's like if you do that, you're just giving yourself more steps later. So I like to get numbers on one side, variables on the other as much as I can. And then we can solve this. 3.38 times 10 to the minus 3 squared divided by 6.8 times 10 to the minus 4 is 1.6 plus 3.38 times 10 to the minus 3. I get question mark. Tell me if this sounds good to you. 0.0202 molarity. Is that the answer people got?
Different numbers.
Oh, different numbers, right? So you might have a different pH, different numbers, but that's the process. All of the answers should be someplace around that molarity, I think.
And then you go from, it's asking for grams. So then you just.
Oh, and then you do molarity times total. Wait, it's asking for grams?
Yeah.
Mine is actually.
Does it give us a volume?
Yeah.
Yeah.
Oh, okay. Okay. Whew. I didn't write down the volume. I was like, this is impossible unless they give you a volume. Volume's given. So you do molarity times volume to moles, moles times molecular weight to grams.
I have a question about one that I was struggling on, but it's not up there, but.
Which number is it?
I think we already, she said you already did it on in office hours earlier, so.
Wait, what was the problem though?
It was the last problem on 2.2. It was about, like, you only got the pH and you were trying to find the concentration of magnesium. And that one, she was saying that, like, it says use the X's small approximation, but you really don't have to use the X's small approximation at all. And it also says look up the, it was like, look up the Ka value on, like, the note sheet, and then the Ka value's not on the note, on the Chem 3 note sheet. Or the KB value, sorry, KB value, because you're doing hydroxides.
Oh, that is because different.
You need KSP for that one.
Yeah, I think it's supposed to be KSP, not KB.
Okay.
Yeah, and the KSP value should be there.
Yeah. Okay. My bad.
Yeah, magnesium hydroxide KSP should be there.
Yeah, that's there.
Okay. Whew. Okay. I was like, man. Okay. Should we look at number 3? Let's look at number 3.
Once I get to this part, I get this Ka, which is like what I have up here, and then I get some funky number right here. So what's going on? Did you? But I don't know how do you involve the pH?
Okay, so it's a new pH.
Yeah.
So that's your new X value.
Oh, like yeah, like I'm not doing it right.
Which one are you working on?
I'm working on like part B of 3.
Oh, okay. Let's look at number 3 together real quick. What's the problem saying?
Mine is.
Yeah, I think I know this one. Go for it.
Beaker with 406 milliliters of an acid solution with a pKa of 5.28 has a pH of 3.
Okay. What's that ask?
It's asking for the initial concentration.
Oh, okay. There we go.
Sorry, I just like disconnected for a second.
So we're trying to find the initial HA. This is actually really similar to what we just did. It's actually exactly the same as what we just did.
Yeah.
We're going to do it for generic acid HA, but we're pretty much going to get Ka. If I did the whole equilibrium table, I'd get Ka equals x squared over HA initial minus x. Where x in this case, I can do this one in my head. This is just 1 times 10 to the minus 3. Right? So I'm going to, Ka is equal to 1 times 10 to the minus 6 divided by, oh, I know the pKa. 1 times 10 to the minus 6 divided by, I'm going to call it question mark again, 1 times 10 to the minus 3 is equal to 10 to the minus 5.28, right? pKa to the power of negative 10 to the power of negative pKa is the Ka value. Then I can go ahead and solve for question mark. You're getting that part right?
Yeah.
What do you get for question mark?
0.19147.
0.19.
Yeah, 147. I'd always leave extra.
1915.
Yeah, that's fine.
191. Okay. So there's our 0.191 molarity. That's our initial concentration. That's for part A.
Yes.
Part B is where it does something weird and it says, hey,
Yeah.
get a different acid. Now read from there because I don't remember the rest.
If you're going to make a solution with the same concentration that had a pH of 2, you would pick an acid with what pKa?
So now, so you notice it's going to be the exact same setup,
Mm-hmm.
except for it's changing out of our 3 unknown things, it's switching which one is unknown. So we're going to have Ka is equal to x squared over HA initial minus x. But now when we plug that stuff in, you said pH of 2?
Yes.
That's going to be 1 times 10 to the minus 4 divided by 0.191 minus 1 times 10 to the minus 2 is equal to Ka. Right, so it just switches which unknowns we have. You're fine. Don't worry about it. So it's just switching around which things we know and which things we don't know. It says, hey, I want this HA to be the same as the thing you just calculated.
Mm-hmm.
I want this X value to be associated with pH equals 2, or a H3O plus minus concentration 1 times 10 to the minus 2.
Uh-huh.
But I want you to figure out what the Ka is for that situation. It's going to be that. Oh, 1 times 10 to the minus 4 divided by 0.181. I can't do that in my head. 4 divided by 0.181 should be a Ka of 5.52 times 10 to the minus 4. Take the negative log of that. pKa of 3.25. Now, does it make sense that we have a lower pKa, that is to say, a stronger acid?
Yeah.
Why?
Because the pH is going down.
The pH is lower with the same concentration. That means the acid must be better at giving away protons. It must be a stronger acid. Question.
I'm just a little confused what you substituted the X for. Like when you did
Oh,
that-
sorry. I was being quick. In the problem, it says pH equals 2, which I could just do in my head to H3O plus is equal to 1 times 10 to the minus 2. I just did that in my head real quick. Sorry about that.
I'm curious what was the, not having a full liter, like we only had 406 milliliters, was that there to just, throw you off, or like?
Not intentionally. In the past, this question had a part C that was asking about the number of moles of acid.
Okay,
I took out part C and I forgot to take out the volume.
okay.
So yeah, I never put information there to throw you off on purpose. It's usually because I take out parts of a question and I forget to take out all of the information that goes with the question.
Okay.
But then it looks like I'm trying to trick you. It's not. I was trying to help you, but you don't see the part I took away. That brings us to 8 and 10. How are those looking?
I figured out 10. I was the one that asked you to put them. I don't know if other people need 10, but
I'm sure they'd love to see it.
8 is just like conceptual for me.
What's 8? Let's
it's-
do 8 conceptually, and then we'll talk about number 10.
It asks like to determine which or whether each ion will form a basic acidic or neutral solution dissolved in water. And
yes.
Conceptual, especially for the neutral stuff.
Right.
Yeah.
So this gets to some of the stuff we were talking about today, some of the stuff we were talking about last time, which is when we dissolve something in water, is it acidic, basic, or neutral? And so we have to look at the parts of the salts that fall apart. Today in class, we were looking at solutions that came out basic. And that was a new thing for us. Usually the solutions we've made in the past, like in 127, 128, they've been neutral solutions. And that's because, essentially, well, neutral or we just haven't thought about it. And it's because we need to consider weak acid and weak base equilibria in order to figure out if these salts are making acidic or basic conditions. Now, the obvious one we haven't had, that we've done before but never had to think about, is if you put magnesium hydroxide or sodium hydroxide, if you put a hydroxide salt into solution, of course it's basic, right? Because you're putting OH minus into solution. But we can make sense of that. That's from the Arrhenius definition. We can make sense of that from the Bronsted-Lowry definition now if we're putting a proton acceptor into solution, right? OH minus is a proton acceptor. That means we can think, okay, what other solids puts a proton acceptor into solution? So we can look at our different solids. If we put in sodium carbonate, turns out carbonate's a proton acceptor. Sodium sulfide, so S2 minus is a proton acceptor. Like all of our anions that are the conjugate bases of weak acids are proton acceptors. And so all of the ones that are conjugate bases of weak acids will act like bases and increase the pH. Sorry, conjugate bases of weak acids will act like bases. I think that's what I said. I'm getting tired. Will act like bases and accept protons, increasing the pH. If we have something that is the conjugate base of not a weak acid, conjugate base of a strong acid, it's not going to have any effect.
So that's when it would be neutral?
Yeah.
Okay.
Right? So think about it. If you put sodium chloride into solution, what would Cl minus form if it was a proton acceptor? If you put NaCl into solution, so you had Cl minus floating around in solution, if we treated it like a proton acceptor, it would form HCl, right? Cl minus would take the H plus, form HCl. You'd have some OH floating around as well. But HCl is a, what kind of acid? Strong acid, really strong acid. So is that equilibrium of forming HCl measurable in any significant way? Nope, it stays as Cl minus in solution. That H stays with the OH, stays water. So that Cl minus, the conjugate base of a strong acid, ends up being neutral.
This is just a vocabulary word. What does monoprotic acid mean?
One proton to give away.
Okay, so it's only like 1-1 ratio?
Yeah.
I kind of assumed so, but thought
Yeah.
you might ask.
Yeah. So that is how we get basic conditions and neutral conditions. You tell me, how would you get acidic conditions? Not a conjugate base, but a
Conjugate acid.
of a
Weak base or strong base?
weak
or
base.
Weak base.
Conjugate acid of a weak base will put H pluses into solution, and that will make acidic conditions. Now, we haven't talked much about conjugate acids of weak bases. We'll be getting into that more on Monday. But in short, it's nitrogen-containing compounds mostly. If you look at your equations sheet, you'll notice it's like NH3 and let me look. You got things like NH3, CH3, NH2, which is that nitrogen on the end again. CH3, CH2, NH2, nitrogen on the end again. OH, NH2, nitrogen on the end again. C5, H5N, nitrogen on the end again, right? That nitrogen with its lone pair, if you remember the Lewis structure for nitrogen, acts as a proton acceptor. And so our weak bases often have those nitrogens in it. Or if we see something that's like a nitrogen with an extra proton, those are going to be the conjugate acids of our weak bases.
With like hydrogen sulfate, how would we know that it's, because that's like one of the ones where it can become like hydrogen.
Polyprotic,
Yeah. So how do you know what way it's gonna go?
Consider the Kas.
Okay.
So if you look at H2S and you look at HS, HS, you can just look at the Ka value, right? HS has a Ka value of 9 times 10 to the minus 8. Could donate, sorry, no, that's H2S. HS has a Ka value of 1 times 10 to the minus 17.
Sorry, hydrogen sulfate.
H2S or HS?
HSO4.
Oh, sorry, I was doing sulfide. HSO4 has a Ka value of 1 times 10 to the minus 2. Gonna donate protons.
Okay.
H2SO4 is a very, even on here, it just says very large. Right, so
Yeah.
H2SO4 isn't gonna form, it's gonna donate protons away.
Okay.
And we're going to get into that. The polyprotic ones really become like a consideration of how well does it behave like an acid, how well does it behave like a base.
So then, wait, so sorry. When you say that the conjugate acid of a weak base will create acidic conditions, so...
Or not just that, sorry. Anytime you're putting a conjugate acid of a weak base, so in that case, so you're looking at that one we just did and being like, is that a...
Yeah, because it, like...
HSO4 2- would be the weak base, and HSO4- would be the conjugate acid of that weak base.
Okay, because it has us start out with HSO4- and just, like, when that's dissolved in water.
Yeah,
it
so
forms acidic.
HSO4- would be the conjugate acid of SO4 2-, acting like a weak base.
Okay.
So technically it is a conjugate acid of a weak base.
Okay, that's just like thinking of how that forms
Yeah,
instead of
and this-
what would
this
happen
really-
when it's dissolved.
Yeah. Well,
Okay.
anytime we're like, so for each of those things we were talking about, we have to think, what's the thing dissolving? What are the possible equals? The same considerations we had on the board in class today. What's in solution? What reactions could happen? What equilibrium could happen? Okay, so you put HSO4- into solution, and you're right, it could donate a proton, it could accept a proton. But when we look at the equilibrium of it accepting a proton, it's like, oh no. Anytime it accepts a proton, it falls right back apart because that Ka value is large.
Okay.
So it's not going to accept protons, but it can still donate protons. It actually donates protons pretty well with the 1.0 times 10 to the minus 2 Ka value.
Okay. So like, sorry, I'm
No, you're
making
good,
this
you're
longer. So like if you had like sodium fluoride.
Yeah.
Um,
Sodium's not really going to do anything. What's F- going to do? Is that going to be a proton donor? Absolutely not. It's got no protons to donate.
yeah.
Proton acceptor?
Yeah, 'cause
How could we tell? What's the Ka associated with HF? Is it a weak acid?
it's 6.8 times 10 to the negative 4.
So that is something that can donate and accept, like that would be a proton donor, which means F- would be a proton acceptor,
Okay.
right? F- is the conjugate base of a weak acid. So F- would have a measurable equilibrium.
Okay.
Base.
Yeah, because it's going to be taking those H pluses out of solution, leaving the OH minuses behind.
So when you have a,
Same question or?
sort of in the same vein,
Okay, go for it.
hydrogen phosphate, H3PO4, and there's just a multiple choice. I said, can it act as a base and an acid, or only as an acid, or only as a base? So with this, I just said both, even though it's incorrect.
Mm-hmm.
But I don't see how it would be theoretically impossible for a proton to hook up to it.
Making H4PO4 plus?
Yeah.
You're stuck on those super acids we were talking about.
Is that the same thing?
Yeah, right.
Okay,
So
so
it's one of those situations where if you look at the Lewis structure for this thing.
Yeah.
Or if you look at the Lewis structure for PO4, what's the phosphate charge? PO4.
5+. 3
PO4
minus.
3-, right? So when we draw the Lewis structure for this, we got 3 spots where we could clearly attach hydrogens.
Yeah.
Without anything really absurd. So H3PO4, where would you put that 4th hydrogen?
Nowhere. But I mean, if it lost H2PO4. Oh, that's why it's asking about H3PO4.
Yes.
Okay, got
It's
it.
asking about H2PO4 could be a donor or an acceptor.
Okay, that's why,
Yeah.
that's what was my confusion.
Yeah, yeah. So it's specifically asking about H3PO4.
Yeah.
Okay, let's go ahead. It was number 10 we still have to do.
I didn't need that one.
I'm good, I'm gonna head out. I
Okay.
appreciate your help. I appreciate you opening the quiz for me last night. That's
Oh,
really-
you bet. Yeah, no worries.
Really
Yeah,
appreciate
I'm gonna
that.
pause this in case we have more questions.